Pete Yost here for the UnBuild It podcast. We have two sponsors this week. First up is Aero Barrier, a new way to air seal homes. Aero Barrier uses a blower door to move non-toxic airborne sealant into all the nooks and crannies where air leaks occur in a building's shell. It's a completely performance-based air sealing system. You get to watch your blower door number drop as the sealant tightens up your building. This technology was first developed for sealing forced air duct systems. And when I heard that the same company was developing a system to seal homes, I was really skeptical. But I have watched highly skilled Aero Barrier technicians prep a home and run the Aero Barrier technology, and it is clear that both the technology and the installation are based on sound building science and a superior understandings of how buildings leak air. The UnBuild It podcast is proud to have Aero Barrier as a sponsor. Check out their air sealing system at www.aeroseal.com. Our next sponsor is Home Building Crossroads, an educational webinar series sponsored by Zip System Building Enclosures and Advantech Subfloor Assemblies, bringing the best speakers in the industry to discuss building science and help you walk away with real solutions to the building issues you're facing. Christine Williamson, president of Building Science Fight Club, will present her course, Airtight Done Right, on 2 dates in December, Tuesday, December 15th, and again on December 17th. Airtight Done Right highlights small design adjustments using standard materials that architects and builders can immediately make to improve airtightness and energy efficiency in residential design. For more information and to register, visit zipsystem.homebuildingcrossroads.com. Welcome to the UnBuild It podcast, folks. Pete Yost here with my colleague Jake Bruton. And we've got a special guest today, Gary Nelson, who is the founder of the Energy Conservatory, producers of the Minneapolis Blower Door system. And this is as exciting and as geeky as you can get. We're really lucky to have Gary. He's got one of the longest creds in terms of looking at air tightness in buildings. And so we're really looking forward to learning a lot more about how blower doors work, what they do for us. And we're going to get pretty techie, right, Jake?
Yeah, nerdy. I'm okay with nerdy on this one.
All right.
That's why I volunteered to sit in. Thanks for joining us, Gary.
Gary, so how about if we start off with a little bit of how you got involved in the building industry and how you blended your technical background with monitoring equipment for buildings?
Well, it's a long story, but I'll try to make it short.
We're all about long stories, Gary.
But I think it's interesting that I was a physics major in college back in the late 60s and early 70s, and I attended a physics seminar one Saturday afternoon that was about peak oil. And it was about M. King Hubbert and his theory of peak oil, and well, it wasn't just about that. It was kind of a discussion about what's going to happen with energy supplies over your lifetime, young student. And, it was really scary. I mean, I was convinced that there were going to be shortages of oil and gas, not coal. There's a lot of coal in the ground. I found this really interesting. But I didn't do anything with it for about 10 years. But then the Arab oil embargo, the first energy crisis, hit in 1974, and I got a little bit more interested. And then in 78, my wife and I bought our first house, and it had problems, and I started researching how to make our house more efficient, and why is the roof rotten, and why are there bad ice dams, and the first winter we lived here, we had really bad ice dams, and I hooked up a hose to my water heater and tried to melt it with my hose, and the hose burst in the basement, and I had hot water all over. And I thought,
Cool.
I should learn more about how do these things work. And I almost finished a master's degree in mechanical engineering and was offered a job at Medtronic that makes pacemakers before I graduated, and I went to work there, and I loved my job. But other engineers that I worked with were real interested in their houses, and I took some courses on energy auditing and how to make houses more efficient. And so we had a lot of discussions at work about this. And even though I wasn't looking for a job, I had a great job. One day I just happened to look in the Sunday paper under, help wanted for engineers, just thinking, well, what kind of engineer jobs are there out there these days? And the state of Minnesota was advertising wanting somebody to do residential energy conservation research and development. And immediately I thought, well, that's what I want to do.
Sure, why not?
Why not? So I called in sick the next day and got an interview and was offered a job like 3 days later. And so 2 weeks later, I was at work with the state energy office, and my job was I was in charge of the technical part of the first big residential energy audit program in the U.S. It was called the Residential Conservation Service, and it required all of the major utilities to offer energy audits to their customers. So I was in charge of making sure that the calculations would be done correctly in Minnesota, and I started researching this, and so I had an unlimited long-distance phone bill account, and I spent a lot of time talking to the country's experts on doing the research on energy efficient buildings, and I especially spent a lot of time with Gautam Dutt, who was at Princeton at the time, where they discovered attic bypasses, and they actually named the blower door, I believe, and the attic bypass, and they came up with the term house doctoring. And
But Gary, up until that point, there wasn't much focus on the contribution of air leakage to building performance, right?
Oh, there was, but people mostly thought, well, it's the windows and doors. You have to weather strip your windows and doors. And no, Princeton was really responsible for discovering that the major air leakage sites in buildings were largely at that time unknown. The leakage of top plates and you would think these days when you go up in an attic in an old house and you pick up a piece of insulation and you can see the basement floor through the soils, with the soil stack going down this 6-inch open wall cavity, you would think that somebody would have figured that out, but largely they didn't, and so that was kind of figured out in the late 70s, mid to late 70s, and they developed the use of the blower door along with an infrared camera, where you depressurize the house with a blower door and then look from the inside of the house to see where do things get cold, if it's colder outside, or hot if it's hotter outside, and the whole idea of house doctoring started then. And,
but that's a big jump from a government job to either starting or running a manufacturing company.
Oh yeah, so I worked on this energy audit program for a couple of years, and then I did a little study on super insulated houses that were just starting to get popular, and I got to a point where I realized if I'm going to learn more, I need to get out in the field, and I didn't have that opportunity, so I quit my job in order to become a house doctor and get out and do things. And one of the things, a good friend of mine was a physics professor at St. Olaf College, where I went to college, and he was doing energy efficiency research, and he offered me a job to be his assistant, and I would go out and put in data loggers and houses that we were researching. And the first project, I got to borrow a blower door and go out to about 50 new houses that were part of an energy efficient housing demonstration program. And I got to go out to these houses with a blower door and an infrared camera and a bunch of other temperature and relative humidity measuring instruments, and try to figure out why did some houses seem to work much better than others. And so that's how I got into blower doors. So after that project was done, we were able to borrow a blower door from the Mid-America Solar Energy Complex. There were these, I think, 5 regional solar energy centers that were funded by DOE, and luckily we had one in Minnesota. So I was able to borrow a blower door from them that was made by Max Sherman. One of the early manufacturers was a company named Harmax. Max's father's name is Harold, and Max is Max, so Harmax blower doors. And so after that project was done, I was motivated to get a blower door. I needed a blower door. I already owned half of an infrared camera. The guy that I was working with and I went together and each paid for half of a used GEMA 720, the old ones where you poured liquid nitrogen into a little quarter cup vial inside of like a little thermos bottle that was built into the infrared camera. It was quite a show. You know,
Gary, do you mind me asking what half a blower door cost in 1979?
No, half an infrared camera.
Not a blower door. Camera.
Half a used infrared camera cost $10,000.
Yeah, I was thinking that range.
I just 3 weeks ago bought a FLIR infrared camera that I can plug into my phone for $350. That's better. And it doesn't need liquid nitrogen.
And you don't have to carry a vial of...
It fits in my pocket, and I take a picture, and it's on my phone, and it's in the cloud, and it's really quite
whole new
amazing what's happened. So anyway, I needed a blower door, and I knew that it had to be lighter than that stupid Harmax blower door. That luckily I had an assistant who was a University of Minnesota football player, and he was probably 6'5" and 220 pounds, and he could lift the thing. I couldn't lift it. And we had the use of a big old station wagon, and he would load it in the back. And
so the blower doors today weigh about 38 pounds or so. How heavy was that sucker? You were...
I would imagine that the heaviest part, which contained the blower, must have been 75 to 100 pounds.
Yeah. That's a backbreaker.
I could barely lift it.
Yeah.
And it was very heavy.
So you built one?
So I built one. I bought for about $100. I could get a fiberglass flow measuring nozzle from Saskatoon Fiberglass. That was designed by Harold Orr. I don't know if you remember Harold Orr. He was at the National Research Council of Canada in Saskatchewan, where they built one of the first super-insulated houses in North America called the Saskatchewan Research House, I think it was. And he designed a blower door so that they could test the airtightness of a whole building. And not many people had tested whole buildings by this time. Actually, there was some research back in the 70s. We could get into that. But so he built a blower door just for their research to help them figure out what was practical to make a new building airtight. Mm-hmm. And Harold Orr became known as the plastic surgeon because of him developing how you use polyethylene and how you cut it and fold the corners and use acoustical sealant and staples and battens and things to make the air barrier airtight on the inside of the building. And a little bit, unfortunately, I think most new houses built in Minnesota these days are still using that same technique of using the 6 mil poly on the inside of the building as the air barrier. But I really think using the sheathing on the exterior makes a whole lot more sense. It's easier and you can get the building a lot tighter, a lot easier, I think.
So Gary, I want to ask you, since we're talking about how you developed or built your blower door, has it always been that you're measuring pressure from the inside to the outside and using a pressure gauge and the fan pressure to get to CFM or cubic feet per minute or airflow? The reason I asked that is because it seems logical to me that if you're trying to do a standard pressure between the inside and the outside of the building, use a digital pressure gauge.
Yep.
But to measure airflow, why didn't you just measure? Why didn't you just use like an anemometer as opposed to a pressure gauge?
The first blower door I used, this Harmax blower door, they carefully calibrated the fan so that they were measuring the RPM of the fan and the pressure difference between the inside and outside of the fan, and using the fan curve to calculate the airflow.
And
then somehow adjusting that for temperature and things, and it wasn't as accurate as it is to measure using essentially we're measuring and using an airflow measuring nozzle or orifice now.
Yeah.
And that just makes it a lot easier. Fan curves, if you drop a fan and you damage a blade or it gets dirty, the fan curve changes, and we don't have to deal with that the way we measure flow today.
Gary, I actually I had one of your competitors' digital pressure gauges.
Yep.
And it stopped working, and I was trying to send it back, and I was having trouble during COVID to get them to give me the authorization to send it back to him. So I thought, well, this is a pain in the ass. I'm just going to open the back door, the one that says, don't you dare open this little door because you'll void the warranty. Because I wanted to see.
That's the first thing I always do is to open those doors. I want to know what's in there.
So I took the protective seal off.
Yep.
And I was so excited because I was like doing something criminal. And I popped it open because I wanted to see how does that pressure gauge measure pressure.
Yep.
And I still don't know because I couldn't take it apart completely. But pressure is a force per square foot, right?
Yep.
And so I'm looking at where the numerous tubes come into what looks like an electronic gadget. And I'm thinking, does it measure the pressure indirectly through some sort of algorithm, or is there actually like a diaphragm there? How does that work?
New pressure gauges, new since 25, 30 years ago, the ones that use the same kind of sensor that we use, which is called a piezoelectric sensor. It uses chip technology. So you start out with a silicon wafer, and they etch on that wafer resistors in the form of a Wheatstone bridge. It's just 4 little resistors that are etched on this silicon wafer. And that silicon wafer becomes the diaphragm. So, and then that gets mounted in a little device. So you seal a little chamber on one side, and you seal another chamber on the other side of this silicon chip. And the silicon diaphragm is the diaphragm that moves. Oh, I remember trying to calculate this. It's like a millionth. It's like a millionth of an inch. It's really, really, really tiny. And these things, although it seems impossible, they've gotten cheaper and cheaper, and they're now like $20 and are amazingly good and repeatable. And then each one, a laser, they calibrate each of these sensors somehow. They apply a pressure and they measure the resistance change on this Wheatstone bridge, and then they use a laser to etch the resistors to tune it to be plus or minus 2%. We don't use their calibration. We in order to get the accuracy that we want, we have to do our own calibration of each unit. And then
so when I mail my manometer back to you guys, do you guys replace that chip with a new one, or is there a different calibration system?
No, we calibrate it. There's a calibration equation that's stored on another chip inside of the manometer. And when you send it in for recalibration, we just readjust. We come up with new parameters and save them to the gauge.
And so, Gary, that might explain, because of the construct of that sensor. I mean, it's amazing to me that you can relatively accurately go down to 1/10 of a Pascal. Yep. But then I can take your digital pressure gauge and make it see 1,000 pascals. I mean, that, if you compare that range to other instruments, we just don't like a torque wrench.
No,
you can't buy a torque wrench that'll go down to, a real tiny measurement of torque to a really big one. So that's amazing.
Yep. And I think internally, the sensor in our gauges is actually the smallest increment of pressure that it's measuring is 0.03 pascals approximately, and it does that 20 times a second, and then it calculates an average. And normally when you turn it on, if you don't set the time averaging period to a higher level, it normally is updating the screen, the readout, once a second. So every second that you see the pressure change, that's actually the average of 20 readings with a precision of 0.03 pascals. And if you set it to 5-second average, it's still reading 20 times a second for 5 seconds. So now you're getting the average of 100 readings that were made at 0.03 pascals, but then converted into a reading that only has 1/10 of a Pascal precision. So, although when you plug it into your computer and you use the TechLog program, I don't know if you've ever used that. It's a free download. That will actually save the higher resolution pressures, and you can record 20 measurements per second with a precision of 0.03 pascals.
So, clearly you're
quite
fascinated.
Amazing.
Yeah, you're fascinated by the physics, but that still doesn't explain why you turned it into a manufacturing career.
That was an accident.
That is the best answer you could have given, Gary. Thank you.
I needed a blower door, so I got this nozzle from Saskatoon Fiberglass, and I attached it to a fan, and I didn't know that, the nozzle was only 8 inches in diameter, and my fan was 20 inches in diameter. And how do you connect this? So I made this really steep cone, and I turned it on, and it was supposed to move like 2,000 CFM of air, but it really only moved like 200. And then I had to read some books about fans and airflow. Yeah. And I, unfortunately, when I was a graduate student in mechanical engineering, I never took fluid mechanics. The one thing that I should have taken was fluid mechanics. Well, heat transfer would have also been sort of useful in my career. No, I never took that either. I took machine design and theoretical and experimental stress and strain analysis and how to design thin shell structures and a bunch of stuff that was all very, very interesting, but has been totally useless to me all my career. And the courses that could have been useful, I didn't take. Oh, well.
Well, Gary, I have a degree in fine arts. So,
okay.
I think we're
cool.
It's the same path here.
Wait a minute. If we're going to get into degrees, my undergraduate degree is in agronomy, soil science, and my graduate degree was in resource economics. So my mother, when I was getting engaged, my mother-in-law said, "Oh, well, Peter studied dirt," and then he didn't think that was, sort of significant enough, so he worked on trash, because my resource economics master's was on how to manage construction waste. So, pretty illustrious.
You were just headed for that rock star lifestyle, weren't you?
Yeah. Well, of all the people I know, I'm one of the few that actually every day I still use the things that I studied in college. I mean, a 2-year physics degree, learning, physics with calculus, and of course I took chemistry and other science courses, but a lot of that has been useful my whole life, and I occasionally even derive an equation and solve it and do things like that. So back to the blower door. So I built my first blower door, and it didn't work for crap. And then I studied a little bit, and I decided, I need a bigger flow measuring nozzle if I'm going to move more air. So I made this I had a sheet metal shop help me make a sheet metal nozzle. And that worked a little better. And then I was tinkering around, and then I made that a little shorter so it could be a little more portable. And then we came up with a really good idea for using plywood to make an adjustable frame. And a nylon cloth that went over the plywood panel. And that allowed us to make this thing all fold up into a fairly small package and get the weight down. And then somebody asked if we would make them one. And then somebody else wanted one. And then the weatherization program in Wisconsin, just across the river from us, they wanted 5 of them. And, we just accidentally started manufacturing. Yeah. And at some point, it was probably 2 or 3 years later that we actually decided, should we actually be serious about being a manufacturing company? And we decided to do that. And I was still, both my partner at the time and I were still both doing a lot of consulting work and doing other stuff, working on building energy research projects and things, but yeah.
So Gary, are you part of, or do you know the full story about settling in on 50 pascals as the standard?
No, I've actually in the last few years done some research into the history of air tightness testing, and that's one thing that I have not discovered, although the first use of 50 pascals, do you know when the first energy code in the world required an air tightness standard for new houses?
Wow, in the world.
I'm going to let you tell it,
and
but
what
I know
country?
it. I only know it because you told it to me probably a year ago.
Sweden in 1975.
Whoa.
Before there were blower doors. There was not a practical, commercially available blower door when Sweden set an air tightness standard, and their air tightness standard, so it was set in 1975, but kind of like our international code, it goes out.
It takes a while.
But then it takes a while to be adopted. Mm-hmm. And this code actually was adopted, I think, in 1978. But for a one-story single-family detached house, their requirement was 3 air changes per hour at 50 pascals.
But they didn't have a way of measuring it?
Well, actually, if you make houses that airtight, so in Sweden back then, and I think this is still true now, most houses were built in a factory. In the factory, there were engineers. Engineers know how to measure things. So they just left it up to the house manufacturer to figure out how to measure it. And I don't think that Sweden has, even though it's still essentially required a standard, they still do not require, I believe, that anybody do testing. But if you build a really crappy building and it's really leaky and you have problems, you can hire somebody to test it, and now the builder's responsibility is to come out and fix it. And it's a whole lot more expensive to fix things than it is to do it the first time. So that they've just figured out how to do all this. But
the takeaway from that is for me, 1978 in Sweden. Please, U.S. builders, quit complaining about 3 ACH 50 for goodness sakes.
And in 75, so a 2-story multifamily building had to be 2 air changes per hour, and 3 and more stories tall, the requirement was 1 air change at 50 pascals, which is kind of where the really good, that's just a little bit leakier than a passive house.
And you think that change in number going down as the house goes up is just a just because they know the size of the house is going to go up and it's going to be easier to get lower numbers?
Good question. No, I think it had to do with the driving forces for infiltration are higher in a high-rise
Stack
building,
effect
and in a multifamily building, tobacco smoke transfer and cooking odors and so on are more important. So they just decided, well, multifamily buildings should actually be much tighter than a single-family building, both because they're taller and more exposed to the wind, and because it's more important, because you don't want to smell your neighbors.
Gary, I was kind of expecting you to say that it was related to the surface area to volume thing, but that's interesting that it's much more practical than that.
Yeah, and we could get into a discussion of that. I really think that we should be, our metric that we use for measuring the air tightness of buildings should not be air changes per hour. Mm-hmm. It's not the volume. I mean, how is it that the air leaks out through the volume? The air leaks out through the surfaces. Mm-hmm. And so the surface area of the house is really the important thing. And you could argue that, well, it really isn't even the surface area. It's all the feet of joints in the air barrier materials that go together to make up the air barrier. But there's so many of those, and it's so hard. It would be so hard to add those all up that doesn't seem like a practical way. I mean, we could have a CFM per foot of crack or something like that as a standard. But I think it makes more sense to use just a flow at 50 pascals, CFM 50, divided by the square footage of the surface area of all 6 sides of the building. Mm-hmm. Now, for a while, the 1988 Swedish code changed their standard from 3, 2, or 1 air changes per hour at 50 pascals to, I wrote down the number, I think it was 3 cubic meters per hour per square meter of total surface area.
So that's a rate. Yeah.
So that is just like a CFM 50 per square foot.
Mm-hmm. Yep.
And in fact, if you do the math, their number of 3 cubic meters per hour per square meter is equivalent to 0.16 CFM 50 per square foot.
Oh, and
so that's like 3 times leakier than a passive house.
Yep.
Something like that. FIAS has a standard for the U.S. of 0.05 CFM 50 per square foot. So this is roughly 3 times leakier than that.
And I remember when we were building Science Corporation, it was what we used to be sort of good was 0.25.
Yeah,
I believe to CFM. So
leakier
than 0.16, but still respectable.
Yeah. Now the standard that gets used, at least in the United States, for commercial buildings was developed by the U.S. Army Corps of Engineers, 10 years ago or so, when the military was ordered to make their buildings more energy efficient. And they came up with the standard for air tightness of their buildings of 0.25 CFM per square foot, but they measure at 75 pascals. So if you would translate that into how much leakage that is per square foot at 50 pascals, that's about 0.19. So the Swedish standard's like 20% tighter than that.
So
in 1988.
More than 40 years ago, they were nailing it in Sweden.
Yeah.
That's amazing.
Yeah. They also had, of course, in 1978, a house built to the code had foot-thick walls, reductions in thermal bridging of studs, triple glazed windows. In 1983, my wife and I went to Sweden to visit her relatives, but we also went, I had a Swedish engineer friend, and he arranged a couple of tours of some Swedish house factories. And we got to go see how they were building factory-built houses at, I think, 3 different factories we went to. And there was a factory that was taking 2 2x3s and sandwiching 4 or 5 inches of high-density mineral wool between the 2 2x3s to make a 2x12 that was thermally broken with 5 inches or 4 inches of mineral wool insulation, all held together with dowels that were glued into the 2x3s. So it was kind of like a Larson truss.
Yeah.
But
like
it was
like
but it was solid, made out of 2 2x3s and mineral wool insulation.
Yeah.
And then they also used eye joists for studs, 12-inch deep eye joists filled with special high-density fiberglass bats that were cut to exactly fit the shape of the eye joist. Just amazing.
Hey, Gary, while we're talking, I didn't know that you were a building science or blower door historian, but I'm not surprised. And I wanted to ask you that I've heard that about the same time that the house doctors in Princeton were working out, attic bypasses and such, that there was a separate program doing noise mitigation around airports that was kind of working on some of the same issues, because managing noise is a lot like managing airflow. And so do you know anything about... I've never heard that the two got together, but I'm pretty sure they were at the same time, and they were going through sort of some of the same discoveries, but for 2 different reasons.
Yeah. I've been very involved with the Minneapolis airport noise program, but that started probably in the 90s. So that was 20 years after Princeton. Princeton was in the late 70s. And, maybe there was a program way back then, but I don't know about it. But It does make sense. I mean, the airport noise program here, one of the things, it's in their specs that when you insulate and seal an attic, an inspector will come out with a blower door and an infrared camera, and they will see no black marks on the interior of all of the partition walls where they intersect the ceiling. And if you can see any sign of cold air coming in from the attic into the house when the house is depressurized and you're using an infrared camera, you fail.
Interesting.
So, it definitely, it's the same leaks that matter for noise and infiltration.
Yeah. So, Gary, there is at least one other major blower door manufacturer. Are there really significant sort of how the systems work, or are they both just sort of high quality manufacturing systems that use the same techniques and principles?
Well, if you look at the two side by side, you realize, somebody probably copied somebody. So, they really look very, very similar. Mm-hmm. And almost all of the things that you will notice about the design are things that we developed. Mm-hmm. They work very similarly. I would say that for just doing a blower door test, I think they're pretty comparable as far as accuracy. But if you want to measure pressures, really low pressures like room pressures due to air handlers running or fans running or something, and you're down there in the 0.1 to 0.3 or 0.4 Pascal range, our manometers does that a lot better, or a lot more stably. It's more precise and more stable and more repeatable, especially at the low pressures. At the high pressures, they're both good enough. But at the low pressures, we've really worked hard on that.
Yeah, that's interesting, because I do use my digital pressure gauge quite a bit to, since I'm in a cold climate, assess stack effect in a building. Yep. And, room to room based on what fans are running. And those are mighty low pressures, or they can be for sure.
Yeah. It's kind of amazing. I just want to put in a word for the work that FSEC has done on duct leakage, and not just duct leakage, but pressure imbalances caused by forced air systems that haven't been totally balanced. Mm-hmm. FSEC figured out, like in the late 80s or early 90s, that if you measure the infiltration rate of a building, a house, with tracer gas, and you get a number, and you then, with all of the interior doors open and the exterior doors closed, you turn on the forced air system. Typically, the infiltration rate of the house that they measured triples. And this is primarily from duct leakage into the attic.
Yeah.
But then if you just close all the interior doors, the infiltration rate triples again.
Oh, I didn't know that. Holy smokes.
And that is just from the fact that in their houses, as in most of the country, you don't have a return in every room. There's typically one or two returns. So all of the smaller rooms are pressurized because there's only a supply in them and there's no return. And the main body of the house, where the living room, dining room, kitchen area is where the return is, that goes negative.
The pressure goes.
And that pressure, it's not duct leakage. It's just the pressure caused by the imbalance of the HVAC system will triple the infiltration rate of the house compared to, doors closed versus doors open with the air handler on. And that still isn't really dealt with very well, although, of course, when we make houses tighter, we probably still have very similar pressures, but now the house is tighter, so it doesn't leak as much. So these pressures aren't as important, but they're still pretty darn important, and I think we should be doing a better job of that. Although I think like Energy Star, they have a requirement that the bedroom pressure measured, the pressure difference between the bedroom and the main body of the house shouldn't be more than 3 pascals. Something like that.
So not only Energy Star, but there was a lot of the energy bill guarantee programs like Masco's Environments for Living. They had this plus or minus 3 degrees difference in any room of the house from the thermostat in terms of temperature, and then plus or minus 3 pascals to go along with that.
So FSEC came up with all these ideas of how to do pressure relief by doing jump ducts over the walls or ducts through the vents.
So we're talking about like Danny Parker and Neil Moyer, those guys?
The work on duct leakage and pressure imbalance was largely John Tooley, Neil Moyer, and Jim Cummings. Danny Parker was probably involved also, but he's been involved more in the mechanical side of things rather than the construction side of things.
So Jake, I've got a whole bunch more questions, but I'm happy to proceed, or you can jump in too, because mine's going to be pretty geeky.
Before we go too terribly nerdy, one of the questions that we talked about beforehand is the aero barrier question.
Yeah.
Another manufacturer that uses your equipment.
They don't anymore.
Oh, okay.
They just recently decided they needed a fan that would work under higher pressure, and they decided they should design their own equipment. Which
I didn't know that.
We've actually been recommending that they do that for about 10 years. AeroSeal, the duct sealing side of things, but now that they're doing houses and they need a more powerful fan, they decided to design their own, or they're actually buying a commercially available higher pressure, higher flow fan.
That's really interesting.
Doing their own. I think they're doing their own electronics.
I would still like to know, Gary, your take on that system, on the idea of pressurizing the house and the aerosolized sealant, and how that affects our industry and just your general.
Well, now that they don't buy from us, I have to say some bad things, right? No, My gut feeling is that if you really design a system like Jake, your system of the zip sheathing and the way you do things, if you decided to go back and do things the way you used to before you developed that system, and then hire somebody to come out and do aero barrier, you would end up with something that might be similar in tightness, but I'll bet it would cost a lot more money. I think if you're a smaller builder where you really have control of the people that are working on your house and the quality that they do with which they do their work, I think you can do it cheaper and just as good. And you know where the air barrier is when you're done. With aero barrier, sometimes it's the sheetrock that's the air barrier, sometimes it's the exterior sheathing, sometimes it might both be the building paper, sometimes it's all of them, or sometime, in this little part of the wall, it's one, and then over here it's something else. And now if you add an addition, what do you seal to? Or if there's a problem and you take things apart, do I have to put this back to be the air barrier or not? Where in your houses, if you ever make an addition, as soon as you cut through the zip sheathing, you got a seal to that. That's the air barrier. And it just makes everything easier. So, but so I did meet with the head of purchasing for one of the major home builders division in Minnesota, and he said he was ready to sign up the aero barrier contractor just because they can't control the quality of the subs well enough. They can't get the poly installed reliably airtight or the sheathing to be reliably airtight, where they can rely on the aero barrier system to give them something that will be better than code.
The majority of the builders in the United States probably don't feel like they have total control with their subs.
Yep.
So, Gary, I think... Go ahead, sorry.
One other quick thing. Where aero barrier really makes sense is sealing up existing buildings with severe leakage problems that you just can't get at.
So you can't take it apart.
Apartment buildings with tobacco smoke odor issues and noise issues, and whenever an apartment changes hands, you go in there and you do an aero barrier job, and you can get the apartments to be really tight. I think there's definitely a market for this.
Well, that's actually what I was going to bring up, which is, I am constantly up against the wall of airtightness is the second most important thing in all buildings, but especially existing buildings. And the only available system to reliably air seal a building is spray foam. That is the default system for people to use. And to me, aero barrier is real because we have 150 million existing units that aren't airtight, is to go after existing buildings. But it's interesting because when I've talked to them about this, they're like, hey, we're having enough trouble keeping up with the new home market.
Yeah.
And yes, we understand that there's potential for existing homes.
Yeah.
But so I think the issue of the fact that these, suspended tiny particles of sealant, they don't decide where to go. So if they decide to accumulate like between the quarter round shoe mold, as opposed to somewhere else, that's what they're going to do. So I think that there's more management and smarts that have to go on with, I was talking to one of the air barrier guys who's doing a lot of existing buildings. He said, I'm inside while this is happening and I'm looking for where it's accumulating. So if I see it's accumulating shoe mold, I'll pull the shoe mold out to get it to penetrate to the layer that I want it to do its job. But that's a lot more, that requires a lot more understanding of how the building works. That requires a lot of sort of hands-on, literally inside the building while it's going on.
Yeah. So I was just reading the 2018 IRC just a couple of days ago, and I didn't realize that it actually says in there that the air barrier shall be on the warm side, the winter warm side of the thermal envelope.
What? The 2018?
I'm pretty sure that was the 2018.
On the warm
I might be
winter.
wrong because I was also reading the 2012 at the same time.
Wow. I did not know that.
Well, we're just going to look in real time. I have the code book.
Yeah.
You guys keep talking.
Yeah.
But then, of course, if you build buildings like Jake does, and the way I did an addition on my house a couple of years ago, where you use the exterior structural sheathing as your air barrier, and then you put a bunch of insulation on the outside of that, that would certainly be allowable.
That would be warm in winter, yeah.
But if you were going to actually enforce that, and somebody was going to use aero barrier, how are you going to show where the air barrier is when you really don't know? It's in a multiple of places.
This is a really geeky question, and I think I tried to ask Colin this question, but it seems to me that if a system like aero barrier is significantly changing the air tightness of the building and the size of the leaks, don't they by definition have to do a regression analysis to adjust the n value of the exponent to get a true reflection of the air tightness improvement?
Well, the requirement in the IRC is 3 ACH50. So you don't have to measure the exponent of the leakage curve. You only have to measure the flow at one pressure, 50 pascals. So I think they could do that. And then, once you get a house down to 1 or less ACH50, it really doesn't matter, I don't think. I mean, you're now down to the point where the natural infiltration is a tiny percentage of the required ventilation that you have for the house. So the energy, there isn't much energy savings to be had anymore, and it's really not affecting. It's not providing ventilation. You have to design the ventilation system to provide the whole thing.
Yeah, but Gary, I'm asking you a measurement question, not. You know what I mean? Like.
Yeah.
So
depends on. So what do you want to measure? You want to know.
If the exponent, the more airtight that you get the building, the more the exponent moves towards 1, correct?
That's not real obvious, but it tends to. The exponent does go up if you test a bunch of tight houses compared to a bunch of leaky houses. But
so if I'm dumping aero barrier in and I'm making it more and more and more airtight, and they do Jake's house down to 0.06 ACH50, my question is, well, if you haven't adjusted the measuring mechanism or calculation, and I agree with you, at that point it's sort of like noise, but I'm just asking about the measurement side.
Yeah. Well, yeah, certainly if you measure two houses at 50 pascals and get the same answer at 4 pascals or 10 pascals, two other pressures that are commonly used for metrics for air tightness of buildings, you'll get different answers depending on the exponent. So, but it really depends on what it is you're measuring. If you only care about CFM 50, then it doesn't matter what the exponent is. If you only care about what the effective leakage area is, which is defined as the size of a hole that would leak the same as the house at 4 pascals, this is in the U.S., this is a common measurement, then because we can't really measure adequately down at 4 because small wind pressure fluctuations are too big, and so we now do the measurement at several different points and we extrapolate. Yeah, now it matters.
Okay.
I mean, getting several data points and calculating the exponent through a regression is the way you measure the ELA at 4 pascals.
And Gary, since the fan pressure measurements occur through taps that are like right in the middle of the blower door assembly. It's always confused me, like, well, how come I've always associated running the fan at sort of an optimal speed as part of minimizing the turbulence of the blades cutting the air, right? And so if I neck down with different rings, doesn't that have an impact on the amount of overall turbulence in the system, or is what happens at the hub really the key?
Yeah, it's what happens at the hub. When I built my first blower door, I would have never guessed that our current design would have turned out to work. I thought the flow measuring part of the blower door really had to be further away from the fan than it does, but it turns out that when you measure in the middle and you do it with the flow sensor that we designed, a mechanical engineer that worked for us for many years, Ron Rothman, designed the flow sensor that we use now, and it's really a good design. But yeah, the way the air flows by it, even when the smallest ring is on, you get really nice airflow up to a point, though. I mean, at some point, if the velocity of the air going into the inlet of the fan is too small, and the pressure difference between the inlet and the outlet of the fan is too big, the fan blades start stalling, and you can actually hear it. You can tell, oh, something's going on here. That fan doesn't sound the same now.
It's like a motorboat cavitating or something, right?
It's a lot like that. And when that happens, the calibration formulas all go to hell. The accuracy, it doesn't work anymore. That's why our gauge, sometimes you'll notice it tells you low fan pressure, or it flashes low. That's telling you the air velocity of the air going into the inlet of the fan is too low, and the accuracy of the fan might be compromised at that point. But you worry about this too much, Peter.
He was right when he said, I'm going to go to a Nerdville place here.
Wait a minute.
Just believe the instrument. As long as the thing isn't flashing low fan pressure, you're okay.
Gary, wait a minute. I am the son of an evangelical Lutheran minister. It's
no.
all about worry and guilt. Yeah. Come on, man.
Yep. No. Yeah. Okay, now I understand you. Nathan, too.
Yeah.
He's referring to my brother Nathan.
Yeah. In looking in the code book just now, I can't find what Gary was talking about.
Maybe
but
that's
in
2012.
my limited experience with Gary, I also agree that it probably is in there, and I can't find it.
Well, it could very well be that it's in an older version.
So, Jake, you know what's really cool is, do you have a hard copy version or a PDF?
I have the hard copy.
So, you know what I do is, I have a 2018 PDF. I will literally type in like warm in winter and search for that way. And one of the things I discovered this way is even the 2018 code, the use of the term vapor retarder, vapor barrier, moisture barrier, it's like you would think that in a document that focused on terminology that they would have gone through and said, hey, look, we have to standardize this term. But like all three are used, and they're different numbers in different places. It's terribly
I'll
confusing.
also say that in the air barrier and insulation requirements, under general requirements, it does say the exterior thermal envelope contains a continuous air barrier.
Yep.
So it does, it definitely makes it seem like it has to be with your thermal barrier as well. That they're making that.
So the other day, I have to ask you a question now. I've been researching garages, and it seems to me that the wall between the house and the garage, it should say somewhere in the code that has to be airtight. And I think in the 2012 code, I found a check box from a DOE presentation about what's required in the code that said, there has to be an air barrier between the house and the garage. I can't find that in the 2018 code.
Nope.
But the 2018 code says that there shall be a continuous air barrier at the thermal envelope of the building. But they don't say, is the wall between the house and the garage part of the thermal envelope? What if my exterior garage walls, like they are in my house, my garage has R40 walls and triple pane windows and a R20 overhead door, and so.
Or what if the garage is heated?
Yeah,
and then it's we're
so what's the requirement?
It probably should be based on conditioned space.
Yep.
And I think that when it used to say that there had to be an air barrier, it was based on conditioned space. But if you have an R40 wall in your garage and triple pane windows and a heater out there,
isn't that conditioned
can you
space?
call it conditioned space?
Yeah, then it's all about your
in the
doors.
ResNet 380 standard, we say even if the garage is conditioned, it shall not be considered as conditioned space.
Wow.
Yeah,
that's crazy.
That's definitely the way it should read for safety reasons, if nothing else. Much less energy efficiency.
Hey, Gary,
so
you're
I've been arguing
way too much about this stuff. You must be a Lutheran, too.
I was.
Well, you combine Lutheran and engineer. I think you have the epitome of worry.
Yeah, okay, right, I got one less geeky question for you, Gary. Good. So, I always do blower doors on houses with the basement door open and the basement door closed. And I'm very concerned that the difference in the numbers is way different than the impact of that volume on the ACH 50. So I'm really concerned that this is kind of bad math. And a big.
Do you alter your math when you close the door? Do you change your volume calculation?
Sure. I mean, if I'm trying, and in my opinion, the real number, since you are not in any way dedicating an air control layer between the basement and the rest of the building, that you have to count that space. It's informative to know the difference. Yeah. But when you do the calculation, you have to include that space.
Yeah. The ResNet 380 standard says that if the basement ceiling is insulated and air sealed, that you then shall close the door between the house and the basement, and the volume of the house that you divide by in order to get air changes per hour does not include the basement.
That makes sense,
but where I'm from, I've maybe seen one house in the last 40 years where they insulated and air sealed in the basement ceiling. And that's really a bad idea, because in the summer you get condensation and your basement's cold in the summer. And you get condensation and it's moldy, and that's a bad idea. And basements should be fully conditioned.
Building Science Corporation did a bunch of research on exactly that. Can you air seal and insulate at the basement ceiling? And I remember Coda saying, and Coda, if he air sealed,
Coda could do it.
Well, even he said you can't. Yeah. You just can't get a decent. Yeah. It's too complicated and too convoluted.
Yeah. And when you've got a forced air system and the furnace or the air conditioner are in the basement, and
all
the ducts run in the basement and they're in the ceiling and they go up the wall. Oh, no, it'd be really hard. Happen. So the ResNet 380 standard says if the basement wall, the exterior walls are insulated and air sealed, then you must open the door to the basement and the basement volume must be included.
Got it. One last.
Same goes for crawl spaces too, right?
Yeah. Similarly, for
crawl spaces, just a short
crawl spaces are. I think I'm reading that right now. The 380 committee is working, and so I'm studying that just to make sure that things are consistent.
I went to Taylorville, Illinois last spring to a tech, not a tech class, a regular high school that has a technology class that they're building their own house, and they're applying a ton of Steve Basic and I's air sealing tactics to this house, and they got a blower door so that they could test, and I brought mine so that I could test for him as well. And he said, well, I think that we're we're just under 1 ACH50. We were hoping for better than that, but I think that we're just under 1. And I said, okay, did you count the crawl space? And he's like, no. I was like, well, the crawl space is conditioned space.
Yeah.
I know it's not technically like directly connected. And so then we added in the crawl space, and they were below passive house, and they were jumping around. They're all excited. I was just like, this is fantastic. I love the fact that just math made my part make them happy.
Now, if there isn't an access door between the house and the crawl space, you probably should also measure the pressure
both ways
difference between the crawl space and outside to verify that it actually is at 50, which it probably is. If you did a good job of air sealing the crawl space perimeter, and you didn't intentionally seal the crawl space ceiling, you're probably fine.
So one more not quite so geeky for you.
Right.
I've been doing a lot of theatrical fogging of buildings.
Oh, yeah.
And I find it's useful in a whole bunch of ways, but I've had clients where I say, here's where the air leakage is. We have to go over after that. It's not, and they say, no, that's too disruptive. So then I show them infrared pictures with the blower door running. No, that's we're not going to do it. And then I pressurize the building and put a fogger on, and they see the fog pouring out of the building. Oh, okay, now we'll go ahead and do that air sealing. So my question for you is, I don't hook up a digital pressure gauge. I just pressurize the building because, rightly or wrongly, I'm worried about the gauge ports seeing the fog. Am I just being a Lutheran minister son worrier?
Yep. You worry too much. No, there's almost no airflow through the tubes and into the gauge. And in fact, if it weren't for the fact that we have these auto zeroing valves that every so often applies, this little three-way valve inside of the gauge opens and closes to supply exactly zero pressure to both sides, or a zero difference across the diaphragm that's sensing the pressure, and then it zeroes the gauge automatically. That's why it's called auto zeroing. So every time that happens, because air is compressible, a tiny amount of air has to move down the tube to replace the air that was lost when this valve opened.
Okay.
But it is so tiny that it would probably take days for air to actually get from the end of the tube into your gauge and down to that valve.
And if I was not just looking at the airflow, but looking at diffusion, that would take years to move down the tube.
Yeah. Now, if you still want to continue to worry a little bit, the side of this, which side, one side of your pressure gauge is open to the room.
Yeah.
Put a 6-foot hose on that, and then because the air containing fog doesn't have to go very far there, although
that's true. Yeah.
There are really tiny tubes inside of the gauge, and even
I know
then,
that because I broke through the seal.
Right. Even then, it really is. We haven't seen a problem.
Well, Gary, you've just I'm sure I'll find other things to worry about, but you're like a therapist.
Well, don't forget to shut off the natural draft water heater before you depressurize the house.
Oh, I learned that trick a long time ago of taking your car keys and putting it with whatever you're, shutting off. And that's worked a number of times. Although, Gary, I did learn that,
How many times have you walked home, Peter, because you couldn't figure out where you left your keys and the clients didn't have hot water?
I'm carrying my blower door on my back thinking, why don't I have my car keys?
Yeah.
No, I learned that you have to call the local fire department when you're fogging houses.
Yeah.
And I was telling Jake that what's cool is when I recently fogged my own house, I called the local fire department and he said, "You're doing what?" And I said, theatrical fog. And he says, "Well, I know all about theatrical fog." And I thought, "Well, you're an energy geek too." He says, "No, we use theatrical fog for all our testing scenarios with our firefighters. For training.
Yep.
Because they don't want to use real smoke, they just use fog.
Yep.
So we had a fog bonding moment over the phone.
Yeah, I had the fire department come twice. It's pretty embarrassing, but both times, they were good-hearted about it, and they understood.
Yeah.
And in your case, did you set off the smoke alarm?
No, I also
or somebody
learned,
saw it.
No, I called ahead of time.
Okay.
But only because once I did get caught by a neighbor, but we nipped them in the bud and they didn't call the fire department. But yeah, the smoke alarms are. Yeah.
Michael Blasnick was using theatrical fog as a tracer gas in attics when he was studying Philadelphia row houses and the attic bypasses and stuff. And he didn't set off a smoke alarm, but it looked like there was smoke coming out of the roof of a building, and somebody called the fire department, and Michael, they heard the sirens coming, and they looked out the door, and here's this fully suited up fireman running for the front door with his axe ready to. And Michael said, "No, it's not a fire." And the fireman said, "Look, I'm a fireman. I know a fire when I see a fire. You've got a fire in your attic."
That's fantastic.
Wow.
But yeah, that's happened to a lot of people.
Yeah.
We should know better, shouldn't we?
Well, yeah, my wife says there's a lot of things I should know better, but
Yep.
Yeah. Hey, Gary, I can't thank you enough for spending some time with us on the UnBuild It podcast. I've known you for a long time, and I've had little conversations with you, but this is way more fulfilling, especially the worry therapy. So thanks a ton.
I have to say thank you as well. The first time that I think Peter gave me your phone number probably 2 years ago when I had some blower door questions, and Peter didn't want to answer my questions. He said, you should just call Gary. And I still to this day, I learned a ton from that conversation. I learned a ton today, and I've never called a manufacturer and just gotten an hour and a half long phone call. I remember my wife coming downstairs into my office going, "Are you almost done?" And I was like, I'm talking to Gary Nelson. You can't and of course my wife's like, "Your kids are ready for you to come upstairs and play with them." And I'm like, "Oh, okay, I'm almost done."
Yeah.
So you've been very generous over the years, Gary. Thank you very much.
And Gary, the DG1000 it sets you guys apart. It's really cool.
Oh, thanks.
Yeah.
Thanks. We've got some other new stuff coming pretty soon.
Excellent.
I'm excited about that. I can't mention now, but I think September and October there's going to be some new things.
We should have plied you with alcohol at the very beginning. We could have gotten that out of you.
Yeah, you probably could.
That's okay. There will be new things out by the time this publishes, because I think we're slated to publish sometime in March of next year.
Wow. Oh, okay. Well, we can
break
maybe
the fourth wall.
Do a little addition.
Yeah.
Or something.
So, okay. Thank you guys for listening. Thanks for joining us today, Gary. I wanted to
My pleasure.
Thank our sponsors for today as well. If you have any questions, you can email us, questions@unbuilditpodcast.com. Don't forget to look up Peter Yost on Instagram. Peter, do you know your Instagram
I remember
handle?
it. It's Building Right Peter with a W.
I'm Jake Bruton, Jake.Bruton on Instagram. The UnBuild It podcast on Instagram. We'd be amiss if we also didn't mention Stephen Basic Architect on Instagram. And Tech also has an Instagram account if you want to follow them as well.
Yeah, that's TEC, the Energy Conservatory.
Yep. We're trying to convince people not to use tech, but to use TEC.
Oh, sorry.
It's the Energy Conservatory that it stands for, and a lot of people have forgotten that, we're really the Energy Conservatory. Tech is just our initials.
Yep.
Well, on that note, thank you, the Gary Nelson.
Thanks, Jake.
Thanks, everybody.
Bye, Peter.
Hey guys, thanks for listening to the podcast today. It's Jake Bruton. I wanted to remind you that because Instagram is hiding recent hashtags still because of the election, we decided to extend the Yeti cooler giveaway to December 19th, 2020. So you have until, let's call it the day before, to enter, and then we will announce a winner. And remember, this is a Yeti 105 cooler. It is a $500 cooler. It has swag from all of the sponsors that we had this year. This is just our way of saying thank you for listening to the podcast. Thank you for helping us spread the word. All you have to do to enter is create a video and post it to your feed, not a story, but your feed. Tag the UnBuild It podcast and use the hashtag UBIP. And for those of you that are not great at spelling, that's kind of our abbreviation for UnBuild It podcast. We get it. It's creative. We came up with that all by ourselves. Enter the contest. We don't have a criteria other than that. Do something that you think is going to convince Steve to convince Peter and I that you won. That's the most important thing, is do something you think is going to be worth a cooler. I don't know what that is either. Good luck.